Okay, good morning everyone. Welcome to lecture 3 on this nonlinear and adaptive control course. Last time we had discussed the preliminaries required to understand this course. I encourage all of you to go back and learn about these preliminaries in detail. So today we will move on to our first adaptive control design. So let us start with a motivating example. So let us consider a mass spring damper system. There is a mass m, there is a spring constant k and a damping constant b, and there is an input force given by f of t. That is represented by small f. Okay. So now let us say that I am not very satisfied with the response of the system. It does not behave the way I want it to behave. For example, if I give a step input to the system, I do not get the required transient response, the overshoot, the settling time. I am not really happy with the response of the system. Now, let us also say that we have a reference model which you can call your favorite system. So, let us say we have another system which has a desired response. So, let us say we have the spring constant is given by Km, the damping constant is given by Bm, and let us say the mass is given by mm. So, let us say that this system has a desired response. So, let us call this as the plant, the first system as a plant. So, the input to the plant is f of t, and let us say that the position x of t is the output, which is the position of the mass starting from 0. Let us say that here for the reference model also I have the position x m of t. So, for the reference model, the input is given is denoted by r of t, and let us say the output is x m of t, which is the position of this of the mass of the reference system. So, since I am not happy with the way this plant behaves, I want that this plant somehow imitates the behavior of this reference model. So, how do we go about making sure that the plant follows the reference model? So, the objective is for the plant to follow the reference model. So, by the way, the mass spring damper system can be used to model many physical systems. For example, the suspension of the car. There are many examples. You can find that wherever you have an inertia, a storage element, a dissipation element, these mass spring damper systems can be used to model such systems. Okay, so it's a practical example that we have considered, and the task is for this plant to have a desired closed loop response. So we can say that the reference model in a way captures the desired transient behavior, right. So you can maybe consider an example that so here for the reference model, let us say the input is a step input and the output is some behavior which I really like, and that is why I want this plant to behave similar to the reference model. So if I use the same input, then I should be able to get similar response or the same response as the reference model. So one way to make sure that that the plant is behaves exactly same as the reference model is to make sure that the mass of the plant is same as that of the reference model, the spring constant of the plant is same as that of the reference model, the damping constant of the plant is same as that of the reference model. So if all these three components of the plant are equal to that of the reference model, then of course the plant behaves exactly same as that of the reference model. So we can look at it a little more closely by looking at their mathematical models. So for the plant, we say that the mathematical model is given by mx double dot plus bx dot plus kx is equal to f, right. And for the reference model, we have xm double dot plus bm xm dot plus km xm is given by is equal to r, right. So let us divide the plant equation throughout by m. So what we get is x double dot plus b over m x dot plus k over m x is equal to 1 over m f, right. Let us do the same thing with the reference model. We divide throughout by mm. So what we get is plus km over m xm is equal to 1 over m r, right. Now of course the objective is for the plant to follow the reference model, that is mathematically given as so the objective here is for x of t to be equal to xm of t, right, for all time. So if that is possible, that's that's the best thing that can happen, because we would like the plant to exactly follow the reference model. So if the position of the plant mass is exactly equal to the position of the mass of the reference model for all time, that will solve the problem. Okay. So how do we make sure that that happens? So of course, as I mentioned, one way to make sure is that b over m is same as bm over mm, k over m is same as km over mm, and f over m is same as r over m. So from here, what we say is, what we see is that we need to change our plant such that it follows a reference model. So which is not always a great thing, because plant is something that is given to you. It's a physical plant which you may not be able to change. If you can change the plant, then of course you can do this. Otherwise, it's very difficult to change the plant, and it can also be very expensive to change the plant. So what is the next best thing that we can do? So the next best thing that we can do here is to design a feedback controller. So the next thing is, can we design a feedback controller f of t such that the plant imitates the reference model. So since we can't make the plant component same as that of the reference model, we would like that we design a control system around the plant and make sure that it behaves similar to that of the reference model. So that is the next question, that how do we design a feedback controller f of t. So for that we can try with a state feedback control law. So let us choose f of t, which is the input to the plant, as a state feedback controller, which is given by kpx plus kd x dot. So in this case there are two states, x and x dot, representing position and velocity respectively. So we choose a state feedback controller kpx plus kd x dot, and since we are trying to track the reference model, we also have a tracking term kr times r. Okay. So the question now becomes, how do we choose kp, kd and kr such that this control system is able to make sure that the plant tracks a reference model. Okay. So for that we have to look at this more closely. So let us look at the mathematical equation for the plant and substitute for f of t. So if you look at this equation, we for the plant we substitute for the controller f of t here, and let us see what happens. So mx double dot plus px dot plus kx is equal to f, which is given by kpx plus kdx dot plus kr times r. So again we divide it by m, and what we get is x dot plus b minus kd over m plus k minus kp over m. So this is x dot plus x is equal to kr over m times r. So this is the plant. This is a closed loop plant equation, because we have substituted for the controller. Okay. Then let us have another look at the reference model. So that is given by xm double dot plus bm over mm xm dot plus km over mm xm is equal to 1 over mm times r. So this is the reference model. Okay. What we have done here is we have just chosen a controller f as a feedback controller, state feedback controller, and now we are trying to see if we can make sure that that results in the plant following the reference model, which is that x of t is equal to x m of t, right. So let us look at these two equations. What we see here is that we can compare the coefficients, right. So if the initial conditions are the same for both the plant and the model, so the initial positions and the initial velocities for both the plant and the reference model are the same. Okay. Then for for x of t to be equal to x m of t for all time t greater than equal to 0, the following condition should hold. And what is that? We just compare the coefficients, and b minus k d over m is same as b m over m m, k minus k p over m is equal to k m over m m, and k r over m is equal to 1 over m m. So, what this gives us is the values of the 3 gains as m over m m. This is this will give k p as k minus m over m times k m, and this gives k d as b minus m over m m p m. So, what we see here is that we can compare the coefficients in the 2 equations for the plant as well as the reference model, and if the initial conditions for both the plant and the reference model are chosen to be the same, then these 2 essentially are the same differential equations, and for all time the solutions of both the systems would be the same. So, this is a simplistic approach that you could follow, and how we could represent this as a control system is we are trying to control this plant. I mean it's a, and the controller that we have used is simply k p times x plus k d times x dot plus k r times r, right. That is the controller that we have used, and the output of the plant is x, the input is u. So, x is of course the feedback, and we also have the reference signal r. So, this reference signal is the same signal that is the input to the reference model. Okay. So, here the important thing to note here is that the gains k p, k d and k r, they come from computation using these relations, right. So, what is that? So, this works in many cases. However, there is a very serious limitation of this method, and that is that to compute these gains k p, k d and k r, you need to exactly know the plant parameters. So, to compute k p, k d and k r, you need to know the exact plant parameters are required to be known, right. And that is a very restrictive assumption, because in practice it is very difficult to compute these parameters. You may be able to do an approximate job of finding out the mass, the damping constant and the spring constant, but it is very difficult to exactly say that these are the plant parameters, and x of t matches x m of t only when these are exactly equal. So, if there is a slight mismatch, then the responses can be very different. Okay. So, just to recap, so here we have designed a controller which we can call as a model following controller, because this enables the plant to follow the reference model. The controller is chosen as a state feedback controller, and the gains Kp, Kd and Kr of the controller are computed based on the comparing of the coefficients of the plant and the reference model, and that needs exact knowledge of the plant parameters. Okay. So, that is the limitation of this method. So, how do we overcome this limitation? That is the challenge. So, I next write what the challenge is. So, we want to design f of t such that the plant follows the reference model without using complete knowledge of the plant parameters. So, in the case of mass spring damper system, the unknown parameters are the mass, spring constant and damping constant. So, can we design a controller such that we either do not use any of these parameters at all, or we only use some of these parameters and not all of them. So, the idea is not to use complete knowledge of the plant parameters. So, that this is where the power of adaptive control comes in. As I mentioned before, adaptive controllers are used in cases where you have plant parametric uncertainty, that is, the parameters of the plant are not known or they change in an unpredictable way. So, we want to take an adaptive control approach to this. So, what I mean to say is that here what we do is we construct a controller for this plant, and then we have an adaptation scheme here. So, this adaptation scheme has a inbuilt logic, an inbuilt strategy to adjust the parameters of the controller. Okay. So, the adaptation scheme's input are the input to the plant, the output of the plant, the desired trajectory or the desired reference signal, and it has some way of adjusting the parameters of the controllers online. So, this is an online process, that is very important as compared to the offline approach that we had seen last in the previous example, where we had also considered exact knowledge of the plant parameters. So, adaptive control, as I mentioned, refers to a set of techniques which provide a systematic approach for automatic adjustment of the controllers in real time. That is very important. So, there is automatic adjustment of the controller parameters online or in real time to achieve or maintain a desired level of control system performance when the plant parameters are either unknown or they change in an unpredictable way. So, this is just a statement which explains the entire idea behind adaptive control. Okay. So, now I move on to the different flavors of adaptive control. So, there are adaptive control comes in two main flavors. One is the indirect adaptive control and the other is the direct adaptive control. So, I want to talk about them in brief. So, let us again consider this plant which is parameterized by the parameters theta p. So, for the mass spring damper case, for example, here you would have m, b and k as your parameters of the plant, and let us denote all of them as theta p, which we call as the system parameters. So, in a similar way, the controller is also parameterized so in by theta c, and in the case of the mass spring damper case where we had used a state feedback control law, the parameters of the controller are Kp, Kc and Kc, Kp, Kd and Kr. Okay, and let us say that the system parameters and the controller parameters are unknown. So, in the indirect adaptive control case, the idea is first to estimate the parameters of the plant and then use that to compute the parameters of or estimate the parameters of the controller. So, first we would like to estimate theta p, let us call that estimate as theta p hat, and using this estimate we compute the estimate of the controller parameters, which is given by theta c hat. So, that is an indirect approach, it is called the indirect adaptive controller. And then the second flavor is a direct adaptive control approach, where the controller parameter theta c is directly estimated as theta c hat. So, the intermediate layer of first estimating the system parameters and then using them to estimate the controller parameters is not present. Here we directly estimate the controller parameters. Okay. So, these are two main flavors. I have a block diagram of the two approaches. So, let us just in brief go through them. So, as I mentioned, the plant here is parameterized by theta p, the controller is parameterized by theta c, and in the indirect adaptive control approach we use the input to the plant and the output of the plant as inputs to an online parameter estimator, okay, which estimates, for the indirect case it estimates the system parameters, and it online estimates the system parameters, and we can denote it by theta p hat. And the important thing to note is that these are updated as time goes on. So, it is not just one value, theta p hat is a function of time. So, as time goes on we get newer and newer and hopefully better and better estimates of the system parameters. And then there is another block which is used to calculate the controller parameters. So, what this block means is that somehow the two are related. So, the controller parameters would be some function of the plant parameters. So, f is some function, and if we obtain theta p hat from the online parameter estimator in the previous step, then just by using this set of algebraic equations we could compute the controller parameters, which are then used to update the controller, and this is the indirect adaptive control approach. Let us move on to the direct adaptive control approach. So, so in this approach the idea is very similar, that an online parameter estimator has to be used, but here the online parameter estimator directly estimates the controller parameters. So, this estimator estimates the controller parameters theta c. So, let us call that estimate as theta c hat, and again as you can see it is a function of time. So, this estimate keeps updating as time goes on, and that so that is why we call this as an online estimator. So, as theta c estimate changes, the controller is updated, and so this is very different from the fixed gain approaches that you might be aware of. For example, a PID controller, a state feedback controller, a lead lag compensator, or robust control approaches. So, all these are examples of fixed gain approaches, whereas adaptive control takes a different view, and it has an so that the common thread between this direct and indirect approaches is that there is an online parameter estimator, which at every instant of time gives you an estimate of either the system or the controller parameters, which are then used to update the controller. So, that is the basic idea behind using adaptive control. The mass spring damper was just a motivating example to illustrate that that adaptive controllers would be useful in situations where plant parameters are unknown. So, now I will talk about the direct model reference adaptive control, also call this as MRAC. So, this is a direct MRAC case, and just for simplicity I will consider a scalar case. Okay, so so let us consider a plant which is given by x dot equals Ax plus Bu. So, here so x is a state which is a scalar, A and B are also scalar and unknown, and let us also assume that B is not equal to 0, and this is for controllability purpose. We would not want this to be equal to 0, because A can in fact be positive, and so this can be an open loop unstable system. So, if B is equal to 0, then you could never stabilize the system. Okay, so this is a plant, and then as we did for the model reference controller case, for this case we consider the reference model to be xm dot equals am xm plus bm bmr. So, this is a reference model which captures the desired performance. And the objective is for the plant in the MRAC case, model reference adaptive control, the objective is always for the plant to track the reference model, which mathematically just means that x of t tracks xm of t. So, if you recall the previous cases that we did, we had in fact gotten x of t exactly equal to xm of t. We will see in this case it is not possible, because we assume that we consider that the parameters of the plant A and B are unknown, and so it is not possible to get perfect tracking. What we could hope for is asymptotic tracking at best, or exponential tracking if we are lucky. Okay, so I am hoping for asymptotic tracking. Perfect tracking, which means x of t is exactly equal to xm of t for all time, cannot really happen here because A and B are unknown. So, we will see how we can at least get asymptotic tracking. So, the objective can be also written in terms of the error. So, let us say E of t is defined as x of t minus xm of t, and the objective is then for E of t to go to 0 as t goes to infinity. Okay. So, to achieve this objective, let us consider a controller which has a similar structure as before. So, the controller u of t, let us say, is given by k x of x plus k r of r. So, here there is only one state given by x. So, this is a state feedback controller, k x of x plus k r of r. Okay, so, the assumption here that we are making is that the states are measurable, right. So, x is in fact measurable. We have sensors to measure the state x. Okay, so, we should be clear what the objective is. We want that the error should go to 0, which means that the plant state tracks the state of the reference model. So, let us look at the error dynamics. Which is E dot is given by x dot minus x m dot, which is A x plus B u minus A m x m minus B m r. So, let us substitute for the controller u, which is given by this expression. So, the closed loop error system is given by. So, why we call this closed loop is because we substitute for the controller, we close the loop. This is the feedback control law. So, E dot is then given by A plus B k x x minus A m x m. Oh, so I missed something about the reference model. So, this reference model that we consider, of course, the most important requirement of any reference model is that it should be stable, right, because we do not want the plant to follow an unstable system. So, for this to be stable, the requirement is that A m has to be less than 0 for the reference model to be stable. Okay. And another requirement is for the reference signal r of t to be bounded. So, we do not want that the reference model should have inputs which are unbounded, they should have bounded inputs, and since the reference model is also considered to be stable. So, the output of this reference model x m of t will also be bounded. So, these are some requirements for the reference model. So, you have to be very careful when choosing the reference model. It should be a stable system which should capture the desired transient performance, and the input to the reference model should be a bounded signal. Okay, so let us get back to our closed loop error system. So, here what we get is plus B k r r minus B m r. Okay. So, here I say that the plant parameters A and B are unknown, but let us for a moment assume that we know A and B. So, just for a moment let us assume that that A and B are known. So, suppose A, B are known, okay, just for a moment. So, then what we can do such that this error goes to 0. So, we see here that we want this error to go to 0, which means that if we make sure that A plus B k x is equal to A m and B k r is equal to B m. So, if we make sure that these two conditions are true, then what can we say? So, if these two conditions are true, then E dot becomes equal to simply A m times E, right, because these two terms cancel off, and this is what we get. Okay, this is E dot, right. So, this is a stable linear system since A m is less than 0. So, E will exponentially converge to 0, right. And here what is the condition? The condition is that we choose k x to be equal to A m minus A over B, and we choose k r to be equal to B m over B. This is similar to the case that we had discussed when the parameters are known, okay, for the mass spring damper case. But the problem is when we say that A b are unknown. So, in this case both A and B are unknown. So, how do we solve this problem for this scenario? Okay. So, since A and B are unknown, we cannot find k x and k r. Okay. But what we can say is that at least there exists these gains k x and k r. So, what we can say is there exists some ideal gains k x and k r such that a plus b k x is equal to a m and b k r is equal to b m. Okay. So, although we cannot find the exact values of k x and k r, we assume. So, this is an assumption that we make in the modular reference adaptive control case, and these are also called as the matching assumptions or the matching conditions. So, the controller can be modified now to have k x hat x plus k r hat r, where k x hat and k r hat are estimates of k x and k r respectively. So, since a and b are unknown, we cannot exactly find the value of k x and k r, but what we assume here is that there exist these k x and k r, although we cannot compute their values, but what we can do is we can at least estimate these values. So, we modify our controller to have the estimates of these gains. So, u is k x hat x plus k r hat r. Okay. So, these assumptions, if you look at this assumption, how severe are these assumptions? So, for our scalar case, they would always exist k x and k r, because we have assumed b to be non-zero. So, you could always find k x to be a m minus a. So, there would always exist some k x and k r, even though we say that we can't find it, but this condition would always hold for the scalar case. However, when we get to the vector case or the multidimensional case, we see that these matching conditions may not always hold. So, that is why they are very important when looking at the model reference adaptive control case. The matching conditions must hold. So, that is an assumption that we make. Okay. So, with this as a controller, the closed loop error system becomes so the closed, when we substitute for the controller in the dynamics. So, the closed loop error system becomes E dot as a m e minus b k x tilde x minus b k r tilde r. So, this k x tilde is simply k x minus k x hat of t, and k r tilde is k r minus k r hat of t. So, these are the parameter estimation errors. So, in addition to the error E, which is our primary objective, we also have the parameter estimation errors, which ideally we would like to be to go to 0. So, suppose if you look at this equation and we say that the parameter estimation errors are 0, then this equation becomes exactly same as what we had in the previous case, which is E dot is equal to a m e. But since k x and there is always we cannot always we cannot compute k x and k r exactly. So, we get these estimation errors, which we would like to minimize. Okay. So, So, how do we design for kx hat and kr hat, because we have mentioned that these are time varying quantities, but we still have not come up with the design for these. So, as I mentioned before in my previous lecture that we use a very rigorous approach through the Lyapunov stability analysis to not just analyze stability, but also to design controllers. So, let us consider a Lyapunov function candidate. We want to see if this controller that we have designed is stable or not. So, now as I mentioned, choosing a Lyapunov function candidate is a non-trivial task, but we can start with some good guesses. So, a good guess in this case would be half e square, okay, where e is the error. So, if you go through with this, you will find that it is not very straightforward to satisfy this, but we can further observe that here we have additional error states. So, what are those error states? The parameter estimation errors. So, let us try and include those also in our Lyapunov function candidate. So, and the another thing is, why do we call this as a candidate is because right now we can just choose a positive definite radially unbounded decrescent function of the error states. It becomes a Lyapunov function only when we could prove that V dot is at least negative semi definite. So, till that time this is just a Lyapunov function candidate. So, it is so V is a function of E kx tilde and kr tilde, right. So, it is given by the sum of squares, half E square plus half kx tilde square plus half kr tilde square. Okay. So, this function, as I mentioned, is positive definite, radially unbounded and decrescent. So, it satisfies all the nice properties of a Lyapunov function candidate. Okay. So, then how do we start analyzing stability? The next step is to take the derivative of V. So, V dot is E times E dot plus kx tilde times kx tilde dot plus kr tilde times kr tilde dot, right. And so, what we can do is we can start substituting for the dynamics. So, E dot we have already found out to be this. So, we substitute for that as a m e minus b k x tilde x minus b k r tilde r. What else? That is it. And then we have so k x tilde is given by k x minus k x hat. So, when we differentiate k x tilde, this term is just will disappear because k x is just a constant, whereas k x hat is time varying. So, what we will have is plus k x tilde minus k x hat dot plus k r tilde minus k r hat dot. All right. So, why this is important is that now we can choose k x hat dot and k r hat dot in such a way that V dot becomes at least negative semi definite, and so that's why this Lyapunov analysis in fact becomes a design tool. So, it helps us design the parameter estimators. Okay. So, this with some algebra you could just write this, and then you have b kx tilde x e minus b kr tilde r e minus k x tilde kx hat dot minus k r tilde kr hat dot. All right. So, the next thing that we have to do is to design k x hat dot and k r hat dot, which are our our estimators of the controller parameters kx hat and kr hat. So, how do we design these such that v dot is negative semi definite? So, let us look at the expression of v dot again. So, here we see that the first term is negative because a m is less than 0. So, this term is good for us. The other two terms, this term and this term, we do not really know the sign of these terms, because k x tilde, x, e, r, they are all time varying and we cannot say what sign they are. So, we would ideally want to get rid of these sign indefinite terms by our design of k x hat dot and k r hat dot, the adaptive laws for k x hat and k r hat. So, we have to design the adaptive laws. So, k x hat dot, if we design as minus b x e and k r hat dot we design as minus b r e, then this will cancel these two terms and we end up with v dot as a m e square, right. So, which is negative semi definite, okay. And since v is positive definite, radially unbounded and decrescent, and v dot is negative semi definite, what we can say is that the equilibrium point, so in this case the equilibrium point is E equal to 0, k x tilde equal to 0, k r tilde equal to 0, is uniformly globally stable, okay. So, another point here is, why is this negative semi definite? Because we do not have negative expressions for k x tilde and k r tilde. So, v dot can in fact be equal to 0 for non-zero values of k x tilde and k r tilde. So, since we are missing those terms, this is simply negative semi definite, and we can conclude that the equilibrium point is uniformly globally stable. So, just to recap, the adaptive controller that we have designed consists of the control law u of t, which is given by k x hat x plus k r hat r, and the parameter estimates k x hat dot is equal to minus b x e and k r hat dot is given a minus b r e. So, although we have been able to prove stability in this case, there is a slight problem, in fact not a slight problem, but there is a critical problem in this case, which is that the parameter estimation laws, they require knowledge of b, which we have considered to be unknown. So, these differential equations cannot be computed, cannot be evaluated without knowing b. So, this design clearly will not work. So, to make sure that that b is not present in the design, we will have to modify this design, okay. So, how do we modify this? Well, let us choose a different Lyapunov function candidate. So, let us modify the Lyapunov function candidate, and let us see if we can do something with that. So, let us choose v to be equal to half e square plus b over 2 k x tilde square plus b over 2 k r tilde square. So, here we have included in the Lyapunov function candidate an absolute value of b in these two terms, and why can we include the term b here? Well, you cannot include b in your controller in your expression for u or your online parameter estimation laws, because those are the equations that you have designed and that you are implementing. However, the Lyapunov function is merely for analysis. So, even if b is unknown, you can still include unknown quantities in your Lyapunov function as long as these are positive. So, that is why we considered b, we do not consider just b, we consider the absolute value of b, because b can be positive or negative. We have not really assumed the sign of b. So, let us see what happens with this choice of the Lyapunov function candidate. So, we find v dot as e times e dot, which is a m e minus b k x tilde x minus b k r tilde r minus absolute value of b k x tilde k x hat dot minus absolute value of b k r tilde k r hat dot. Now, can we modify our adaptive update laws such that we cancel these two terms here which involve b? So, that is why I mean we have chosen mod of b in the Lyapunov function candidate, because this gives us an opportunity to modify the update laws such that these two terms can be cancelled. So, our modified adaptive laws can be given as k x hat dot as sine of b minus of sine of b, and then we have x and e. Similarly, k r hat dot is given by minus sine of b times r n e. So, of course, here we assume that the sine of b is known. So, that is a less restrictive assumption than saying that we exactly know b. So, if b is exactly known, then of course, you could use the update laws that we had designed before if b is exactly known. However, if you say that b is not known, but I at least know the sign of b, that it is either positive or negative, then these update laws result in v dot to be a m e square minus b k x tilde x e minus b k r tilde r e minus mod of b sine of b k x tilde x e plus mod of b sine of b k r tilde r e. So, mod of b times sine of b gives you b. So, this term exactly cancels with this term, and this term exactly cancels with this term. So, what we end up is v dot is equal to a m e square, which is negative semi definite, and we can make the same conclusion about the equilibrium point, which is that the equilibrium point is uniformly globally stable. Okay. So, we stop at this point. There are some more details which we still need to cover in this case, and then we also do another case which is the indirect adaptive control, indirect model reference adaptive control case. Okay. Thank you.